Okay, well, thanks. I'm happy to be here to talk about some of my recent work in semantics using probabilistic logic, and particularly trying to combine logical and distributional approaches. So first, I want to thank my colleagues. So this is very much joint work with a faculty member in our linguistics department, Katrin Erk. Her and I started talking about these ideas quite a few years ago, and the main PhD student has been working with both of us on this is Islam Beltagi. In fact, I was just back in Austin. I had to make a quick trip back to Austin last week because Islam just did his thesis proposal on the work related to this. This thing never wants to work when I want to use it. Okay, so I came out of the logical paradigm of AI originally. And I know at least Oren remembers this old stuff. He's not quite as old as me, but not too far behind, I think. Where you tried to represent knowledge in a binary symbolic logic, such as first-order predicate calculus. And you know, as a student, I learned why this is such a great thing. It's a very rich representation that handles arbitrary sets of objects with properties and relations and quantifiers. But the thing that has made this less popular in recent years is it doesn't really handle uncertain knowledge, and it doesn't really do probabilistic sorts of reasoning. And so I think mainly for those reasons it sort of has gone out of favor. I mean, I think maybe the people here are a little bit more old school and still appreciate this stuff. I think a lot of modern machine learning and NLP people really don't appreciate the value of logic at all, which I think is unfortunate, but nevertheless. So just some more on the history. Anyone who knows me, I like history of science and technology. And to me, the sort of applying logic as a semantics of natural language, I mean, arguably it has a tradition going back to the Greeks, but a very influential person in this whole area was a philosopher by the name of Richard Montague, who did some work in the late 60s and early 70s trying to show that you could actually map natural language into formal semantics and first-order logic by using Church's lambda calculus of functions as sort of the fundamental underlying sort of mathematical representation. And he's also most famous for introducing the idea of semantic compositionality, that once we have a syntactic structure for a sentence, we can compute a meaning for each phrase or each constituent in the sentence by computing a meaning from its parts and then assembling recursively a meaning for an entire sentence by working up the parse tree and computing meanings for larger and larger constituents until you get a representation in logic of the entire sentence. This came to be known as Montague grammar or Montague semantics. This is a textbook that I used. I actually did take a linguistics class in semantics as a graduate student way back in the 80s, and we used this textbook on Montague semantics to sort of talk about this stuff. So, and it sort of worked its way into computational linguistics in various ways. But more recently has not been particularly popular because of this, again, the sort of realization that logic has issues. Again, on the history side, I can't help but mention this really interesting book about Montague called Semantics and Murder. So I think if you do a web search on those two words, semantics and murder, only this will come up because it's the only thing I think that connects the two. This is actually a fictionalized account of his death, which was quite mysterious. He died under very bizarre circumstances. He got his philosophy degree at Berkeley, and then he became a faculty member at UCLA. And he died in LA in 1971 in a very bizarre way. I'll just say it's unclear whether it was homicide or homoerotic asphyxiation. If you don't know what that means, try to compositionally compose its semantics from its individual morphemes. I won't go into the details. So it is an interesting book, and he did die under very bizarre circumstances. So a lot of what I've worked on over the last 15 to 20 years is semantic parsing. I just remember Oren coming up to me after one of our first talks. John Zelli gave a talk. It was some AAAI. I don't remember where this was. And you came up and you go, oh, wow, this is really cool. This is interesting. This was like 96, I think. So I remember you being at that talk. And so I've been working on this area of semantic parsing on and off, I guess, over that very long period of time. And I tend to define semantic parsing as mapping a natural language sentence to a detailed representation of its complete meaning in a fully formal language. And here I have the subbolus as a rich ontology of types, properties, and relations, and supports some form of automated reasoning or execution. So, and this whole area was relatively unpopular until recently. And one of the things that, fortunately or unfortunately, I'm famous for is a former student of mine, John Zelli, and I put together back in the mid-90s this small data set on application of semantic parsing to database queries called GeoQuery, where we had a small database of facts about US geography, and the idea was you could take a question in English, like what is the smallest state by area, mapped it to a formal logical expression. We originally used like a prolog expression, and then give that to a database and get the answer out. So, there was a semantic parsing workshop that Yoav and several others organized this summer at ACL. It was surprisingly popular. I thought there was going to be 30 to 40 people there. There was 120, I think, was the registration. Was that right? I talked a little bit more about the history of this. This problem of database queries goes back at least to the early 70s or late 60s with Bill Woods, and sort of that was why I was originally interested in it. But I got interested in the problem of learning semantic parsing. So I've done a lot of work in the past on mapping sentences to logical forms, particularly using machine learning techniques to learn how to do that automatically to make it more robust and adaptable. But that style of semantic analysis has become more popular just within the last few years. But what's really more popular in semantics and language these days is what's usually called distributional or vector space semantics, where we try to represent word meanings, and now people try to do this for even phrases or full sentences or documents, of course, you can represent as vectors as well. So you represent meaning as some point in a very high, usually high-dimensional Euclidean space. And the dimensions encode aspects of the context in which the word appears, like such as how often it co-occurs with some other specific word. Anyone who's heard anything about distributional semantics knows this famous phrase from Firth, you will know the word by the company that it keeps. So it tries to represent the meaning of a word by other words it appears in, the syntactic context in which it appears in, all sorts of different features you can encode as dimensionals in this space. You might want to do dimensionality reduction afterwards or not. And then you define semantic similarity as distance between points in that semantic space. And of course, the last 5 years or even 10 years has seen an explosion of different techniques for doing this. The original is probably something I'm sure most of you have heard of, latent semantic analysis, which was introduced back in 1990. And Sue DeMay, who is one of my now colleagues at MSR, was one of the originators of that approach. But now there's a lot of different approaches for how to do this. I mean, you could give a whole tutorial on all the different approaches. But again, the bottom line point is then words end up being points in some space. So imagine we reduce this to just 2 dimensions. Then you might get something that looks like this, where words that are similar, like cat and dog, are close together. And robot is somewhere between a computer and a man or something. But cat and rock are hopefully fairly far apart. Okay, so that approach to representing meaning has become quite popular. And it has a nice robustness. You can automatically compute these representations of the meanings of words from just large corpora by analyzing the context in which those words appear. But I think one of the issues is how does it deal with compositionality? You can represent individual words or maybe short phrases by the context in which they occur, but how do we represent meanings of larger phrases and sentences? So even more recently, there's been a lot of interest in doing sort of distributional semantics using compositional approaches. So we can actually build up distributional representations of larger and larger phrases and sentences and maybe even complete documents. And there are a lot of recent proposals for that. Again, there's been an explosion of work in that area, particularly a lot of it's moved into sort of more sort of higher order linear algebra like tensors to do this sort of stuff. But I don't think any of those proposals really capture the richness of compositionality you get with something like Montague grammar and logical representations. There was the best paper at StarSem. So StarSem is this new sort of workshop. I guess this year was maybe the third or the third one, I think. But it's a new workshop that last year when it was in Atlanta, the best paper was by Ed Greffenstedt, who did some theoretical analysis, showed that even with these most complicated tensor-based approaches to doing compositional distributional semantics, you really don't get the full power of first-order logic. You can't encode all the richness of first-order logic in these sort of tensor sort of approaches. So at a meeting at the University of Texas, we were reading yet another paper on people trying to compose meanings of entire sentences into vectors. And I uttered this now famous phrase, you can't cram the meaning of a whole sentence into a single vector. I put some profanities in there. You can guess what those might have been. I don't do the profanities.
Distinct profanities?
Yeah, they actually were, so you can guess. I think there were 2 distinct ones. I was jet lagged at the time and was getting upset with reading yet another one of these papers that tried to do this. Yeah, so now I have to keep quoting this because now I've become famous for this phrase. So I guess this was in my talk that I gave at this workshop this summer. Someone tweeted it. It got popular from there and ended up on Hal DeMay's blog. I responded to it there. So now like no one's going to remember me except for the fact that I said you can't cram the meaning of a whole sentence into a single vector. Okay, so I think the interesting thing to do is to try to combine these two. So I've been interested in sort of combining logical and sort of probabilistic methods for a very long time. And there's just starting to be some work in this area. In addition to my own work that I'll talk about, there's also been some work. Hoifeng Poon, who did his thesis here with Pedro Domingos at UW, now he's over in the NLP group with me at MSR, where I am temporarily. He did this work on so-called unsupervised semantic parsing, which is sort of like that because it builds predicates from sort of distributional representations. Mike Lewis, who just showed up here, apparently he's going to be doing a postdoc at UW, and I guess spending some of your time here also. Just finished his thesis with Mark Steedman on some things that sort of create ontologies by clustering based on distributional information. But at the end of the day, they both represent things in sort of a traditional first-order logic representation. It's just that representation and the predicates in it is sort of constructed from distributional information. What we've been looking at is how do we maintain this sort of gradedness and uncertainty in the final semantic representation, not try to put everything eventually into first-order logic. Again, I went through this transition where AI switched from being based on logic to being based on probability theory. And so the sort of major paradigm within AI today is more on the probabilistic side, where we represent knowledge and data as fixed set of joint random variables with a joint probability distribution. And that's great at handling uncertain knowledge and probabilistic reasoning, but it's hard to get these techniques to handle the sort of richness of sort of ontology of types of things that logic has in terms of having objects and properties and relations and quantifiers and all the good stuff that we're used to in logic. So quite a long time ago, this sort of tradition came about. The first workshop on this was actually in Austin, Texas at AAAI in 2000. I don't know if anyone was here. Was it AAAI in 2000 in Austin? No. Yeah, Pete was there. The first workshop on statistical relational learning. And then later this book came out. This book is from like 2005, 2006, I think, something like that, which try to integrate methods from predicate logic or sometimes relational database sort of representations of relations with probabilistic graphical models so that we can do the sort of uncertain reasoning that we're used to in graphical models, but do it with structured multi-relational sorts of data. And so there's been a lot of rich approaches that have evolved out of this tradition over the past 14 years or so. This is a little bit of what Lisa Gator has this great slide she called the alphabet soup at one point of all the different acronyms of formalisms that people have constructed to combine probability and logic. And this is just, I call it a taste of the alphabet soup. So there's stochastic logic programs, SLPs by Muggleton, probabilistic relational models was Daphne Kohler's early work. Bayesian logic programs, I've done some work on that. That's Kristen Kirstein and Luke Durrett's stuff. And then Markov logic developed here at UW. So Matt Richardson's now at Microsoft, and Pedro, of course, is still across the way at UW. They developed the Markov Logic Networks. And then most recently, we've also been using this other probabilistic logic lately that Lisa Gator and some of her students recently put together called PSL, Probabilistic Soft Logics. And so those are the two that I'll be talking about in here that we've been using as basis for semantics in language. Okay. And particularly, I tend to like these SRL methods that at the end of the day, they're sort of high-level programming languages for programming very large graphical models. And you can look at some of these, and basically they're doing that. And so, you know, MLNs are basically a full first-order logic approach to sort of defining abstract templates for complex Markov networks. BLPs are sort of a similar thing that use sort of Prolog to encode Bayesian networks. McCallum's factory, if anyone's familiar with that, is sort of a more object-oriented approach. And then there's sort of functional approaches to this too. Noah Goodman and Josh Tenenbaum's work on Church is sort of like that. But so I'm not particularly religious about which probabilistic logic. I'm very religious about using some form of probabilistic logic. I think all of these have their strengths and their weaknesses currently, which is why currently we've tried a couple of different things. Okay. So again, what our main focus has been is how can we represent semantics formally in a probabilistic logic? And as I said, we've used two of these, either Markov logic or probabilistic similarity logic. And we have a number of papers on this. If you're interested, you can look at my website. Again, my student Islam Beltagi is the first author on both of these. And my colleague Katrin Erk, we called one of our papers at the StarSem conference last summer, Montague meets Markov, because I thought that, again, being a fan of the history, it's sort of trying to combine some of the ideas that come from more probabilistic approaches like Markov originated with the more logical approaches that Montague did. Okay, so I assume a lot of you are familiar with Markov logic. I'm just going to do a couple of slides for maybe the couple of you that are not familiar with MLNs. So again, this was a technique for encoding probabilistic logic developed back in 2006 when, as part of Matt Richardson's thesis at UW, where you have the sort of normal clauses that you expect in first-order logic, but you can weight them. So they don't have to be absolutely true all the time. They're sort of, they have some strength of truth. And a larger weight indicates a stronger belief that the clause should hold. And then you can view these as templates, as I said, for constructing Markov networks. So this is Pedro's probably favorite example that I always use because it's short and sweet, which is the infamous friends and smokers example, where maybe we have two clauses. One says if you smoke, you get cancer. The other one says if two people are friends, then they have similar smoking behavior. And maybe you believe the second one a little bit less, so we give it a weight. And these numbers can be any real value. It's just a question of they eventually everything gets normalized into a probability distribution. So what you do is say you have a couple of individuals in the world. You construct the whole set of ground tuples that you can get from that, and then these rules define dependencies between those ground literals in the logic. So the first rule defines dependency between A smoking and A getting cancer, the other one between B and B getting cancer, and then the friends rule sets up dependencies between smoking of friends, including being a friend of yourself. Okay, sorry. So you can just view a Markov logic program as an abstract template for defining potentially very complex, very large graphical models. And typically the way these things work, you actually do ground them out into a ground network and then do inference on that. But that could get very explosive because if you have lots of individuals, the size of that network can grow combinatorially. So there's all sorts of lifted techniques that try to do inference on these graphical models without ever having to explicitly construct this whole combinatorial space of atoms. Which that's been something that at the recent statistical relational learning conferences have been very active. There was almost a half, or 90%. Was anyone at the statistical relational learning workshop this summer at AAAI in Quebec? So I was there. And there was like 80% of the papers were on lifting techniques to do inference efficiently without grounding this whole network out. So that's sort of one of the hot topics within, not just MLNs, because a lot of probabilistic logics have these similar sorts of issues. Okay, and then that defines a probability distribution over the truth values of all those propositions, where I'm not going to go into the details of this equation, but you basically put in the weights of the formulas and the number of groundings of a formula that are satisfied in the current current world, where a world is an assignment of truth values to all these ground propositions. And basically, I like to view it as a possible world becomes exponentially less likely as the total weight of all the grounded clauses it violates. So, you know, a world doesn't have to satisfy all the logical clauses, just the more highly weighted clauses it violates, the less and less probable that world becomes, because you now get a probability distribution over the truth values of all these propositions, which is sort of nice. And over the years, there have been well-developed inference techniques that you can give it some set of facts, and you can compute the probability. So say I know that Anna is Bob's friend, and Bob smokes. Well, what's the probability that Anna has cancer? Well, there are standard graphical model inference techniques that we can do to estimate this, such as Gibbs samplings or belief propagation. And the real issue is when we have a very large network, how do we do this without grounding it out explicitly? And like I said, that's one of the big current research issues in statistical relational learning. And there's all sorts of learning algorithms for Markov logic, right? I can use expectation maximization, various max margin techniques, various online algorithms to learn both the clauses and the weights on the clauses. In particular, I've done a lot of work on structure learning, because I did a lot of work in the early 90s on this whole other area called inductive logic programming. Some of you might be familiar with that. And there are various techniques for learning both the clauses and the weights. Okay, so I think even Pedro would agree. I've done more work on Markov logic than probably anyone outside the University of Washington. And you know, I really appreciate, I was an early advocate. I remember I became a fan of MLNs. The first talk I saw Pedro give on them in the mid-2000s sometime, 2005 maybe. And one thing I like about it is it fully subsumes first-order logic. All you have to do is set all your clauses to have infinite weight, and now you're just back in normal first-order predicate land, like we're, you know, as a traditional AI person I was used to. And it fully subsumes probabilistic graphical models. Anything you can represent as a graphical model, you can encode that as a Markov net, and therefore represent a joint distribution over an arbitrary set of discrete random variables. Now that clause, those could get very big in the general case, but it's still possible theoretically. And it's nice because you can sort of utilize prior knowledge in both symbolic and probabilistic forms. If I remember hearing the story from Pedro, how he got into this originally, he was trying to combine multiple independent, partially contradictory knowledge bases. And he wanted to have a sort of probabilistically coherent way to do this. And that's what eventually was the impetus for the construction of Markov logic, which I think is great for semantics in language because you have lots of sources of very, knowledge of various levels of certainty and probability. And we want to be able to mix all those knowledge sources together into one uniform representation and do sound probabilistic reasoning over that, which I think is one of the things I really love about MLNs. And there's a large base of open software. There's the Alchemy that comes out of UW, but there's other people who have built implementations of. I've had several people who now have other alternative implementations of MLs trying to get me to convert, but I currently still use Alchemy. But of course, every weakness slide has to have its corresponding. Every strength slide has to have its corresponding weakness slides. So it's so general. That's great, but of course it inherits the intractability of both logic and probabilistic inference. So anyone who knows logic knows inference in first-order logic is semi-decidable, and inference in graphical models is piece-based complete. So neither of those are quite hard enough as a computer scientist, so we have to make something that subsumes both of those. So in general inference in MLNs is just horribly intractable. A lot of people complain. They'll download Alchemy, they'll put in some clauses, they'll try to get something to run, the thing will blow up to hell, and they won't run out of memory or something will happen. Like I said, so there's a lot of current work trying to fight this, right? I mean, basically, since the invention of MLNs, people have tried to do better and better at building approximate inference algorithms that can solve real problems in less than geological time. And like I said, there's a current lot of interest in these lifted methods that you never even have to ground out the explicit ground network in order to do inference in these models. But the progress is, I still think, somewhat slow. So this is one of the reasons why we made somewhat of a switch at one point. Yeah, sure.
I feel like there's an elephant in the room, but now that you're talking about the weaknesses, I want to at least ask about it, which is, it seems like one key thing you'd want from these representations, whether it's MLN or PSL or whatever TLA it is that you'd want to be able to easily map from natural language to that representation.
Sure.
And if you claim that it's a good representation, presumably that mapping would be easy, but you haven't really, well,
it's not easy, and that's never going to be easy. But we're basically just buying into the whole semantic parsing framework and Montague semantics in order to do that mapping. And I'll talk a little bit about that. We use this tool called Boxer, which was developed by this guy named Johann Boss. I don't know if you know Boxer, but yeah. So you might argue that, well, that's the downside of using these logical representations is they're not so easy to get from language. But I mean, I think the upside of them is also strong in terms of being able to represent the actual structure and the logical connectives and the quantifiers and things that you get with Montague grammar. So like I said, I'm definitely buying into the notion that you can, at some level, anyway, we'll go into the details. But you've seen some version of this before anyway. But yeah, that's a fair point. I'll talk about how we do the logic, map from language to logic in a little bit. But it was the inference problem I was talking about. It was killing us so much in trying to do things with natural language with these things that my students started looking at this new formalism developed by Lisa Gator and a number of her students called PSL. And it was built with efficient inference in mind. So inference is designed to be polynomial from the get-go of the formalism, which is one nice thing about it. And it's, again, a sort of weighted rules in first-order logic like you get with a Bayesian logic program or a Markov logic network. But MP inference, most probable explanation, or inference is a linear programming problem. So you can find the most likely truth value on a set of propositions in not in linear time, but using linear programming, which is at least is polynomial, and they're very good packages for doing linear programming very efficiently. So this is just a slide that sort of outlines some of the differences. So one, theoretically, I still like MLNs much better, but the sufficient inference property of PSL gives it certain advantages in my mind. So, but one of the strange things about PSL is we're no longer in sort of Boolean logic land at all. Atoms have continuous truth values in the interval 0 to 1. So atoms are neither true nor false. In previous talks, I've used the word truthiness to refer to this because I'm a Stephen Colbert fan, for those of you who watch Stephen Colbert. And it inherits a lot. The word soft comes from of course, there's a whole area of soft logic and soft computing, which usually is associated with fuzzy logic, right, where you do this sort of thing. So it inherits sort of some stuff both from fuzzy logic and from graphical models. And it inherits from fuzzy logic the idea that propositions are neither true nor false. They have some degree of truth. And these are not probabilities. We're actually going to have probability distributions over truth values, where truth values are continuous between 0 and 1. And the inference finds the truth value of all atoms that satisfy the rules and the evidence. But those are going to be continuous truth value. We're not going to be assigning true and false to these atoms. They're going to be some real value, which is why it turns into a linear program, right? Because it becomes so continuous optimization rather than discrete combinatorial optimization, which is what makes inference more efficient. And yeah, so typically what you do is most MPE inference where you find, well, what's the highest probability truth values on all these propositions that I'm reasoning about, and you can treat that as a linear optimization problem. Whereas in most probabilistic logic, that becomes a combinatorial optimization problem. And so it's computationally more complex there. So that's where PSL has some advantage. Here's just one example of I think this comes from their introduction on PSL, where you say you have two rules. This is actually a good example for today. Hopefully you all voted. I voted by mail for the first time in like 30 years from when I was in college. So hopefully you've all voted today or will vote. So if you have a friend who votes for somebody, then you'll probably vote for them. And the other one says if you have a spouse and they vote for someone, you'll probably vote for them. And it says, well, you're more likely to agree with your spouse than your friends. I don't know if that's always true, but at least it is in this program. And say you get some set of evidence. So this I function is the thing that assigns a continuous truth value to every proposition. So say we know absolutely that John and Alex are friends and Mary's John's spouse, and that Alex voted for Romney and Mary voted for Obama. Then it actually will say that the most likely truth value, so if you do MP inference on this program by the formulas that I think I'll have in a minute, that it will say that, well, John will vote for Obama because he loves his wife more than his friends. Okay. And again, it inherits a fair bit from fuzzy logic. So you actually use these sort of interpretations of logical conjunctions that you typically see in fuzzy logic. I guess this is some Polish guy, Łukasiewicz. Is that the right way to say that? Where you sort of use max for and min for or, and then 1 minus for the truth value of negation. And then you have, for every rule, you have a so-called distance to satisfaction. So if you have a rule L1 implies L2, we say that rule is satisfied if the truth value of the antecedent is less than or equal to the truth value of the consequent. And then we have what we call distance to satisfaction, which is max between 0 and the difference between L1 and L2. So if something's not satisfied, it can be a certain distance from being satisfied. And what the inference tries to minimize is it tries to find the interpretation that minimizes the total distance of all the rules from being satisfied. Okay? And it turns out that turns out to be a linear program. So here's the density function defined in PSL. It says that the probability of an interpretation is this normalized exponentiated version of looking at all the rules, factoring in their weight, and then looking at their distance to satisfaction. So that's why it turns out to be a linear optimization problem, because then we just need to find the interpretation that maximizes this formula, which then you can show just reduces to a linear optimization problem. Okay, so that's one thing nice about PSL is the inference is a lot more efficient. Okay, so enough on all the background. So that sort of provides all the background of the various things that we build on, and now I'm ready to finally talk about what we've actually been using this so far. So again, the whole idea is to combine first-order logic sort of semantics with distributional semantics. That's one of the original motivations we had for this work. And I've sort of already explained why I think that's a useful and interesting thing to do, and do that in the context of probabilistic logic. And for various tasks within this, we've used both Markov Logic and PSL. And the whole idea of this is, can we take distributional information that we typically get in distributional representation of semantics and map it to rules in first-order logic, but those rules are not hard rules as in traditional logic, but they're sort of soft inference rules. So here's the basic architecture of our overall system, is we take two sentences in, and this is the initial mapping to a logical form, as the usual term is used in linguistics. And that we use this system called Boxer, which is based on CCG grammar, which is very popular in semantic parsing these days, thanks to Luke Zettelmeyer's use of it in a lot of his semantic parsing work. But Johan built this thing that just, the predicates are just words. So we're not doing actual semantic parsing in my term because we're not mapping to a formal ontology. The predicates are just words in English. But that means that we don't have any axioms relating those predicates because they're just whatever arbitrary words we appear in language. So this is where I think there is some compromise between a standard sort of semantic parsing where you have a fixed ontology. There's a difference between sort of information extraction as people define it with a fixed ontology and open information extraction, right? You just let the language be the predicates, right? I mean, so you're used to that as anyone. But then how do we do inference with those? Because we don't have formal axioms defining into some formal ontology. Well, so that's what we're going to use distributional semantics for. So then those two logical forms we're going to take some vector space. One thing I like about this framework is it's modular. I actually believe in the framework much more than I do any individual component. So, Boxer has its serious limitations, right? I mean, I've talked to Luke about, he's done this recent stuff where you sort of map to a language-based representation, then do this ontology mapping to map it into a formal ontology like Freebase. And I've talked to him, well, can you give us just a better Boxer, right, that just maps to the logical form with just the English words in it? And, I mean, he thinks maybe eventually he can do that, and I think I would probably prefer that. But Johan continues to work on this, and he's generating new versions of Boxer, and it's getting better. But if you have a better way to just get logical form in a sort of Montague semantic style from language, I'm happy to use it. But then we take those logical forms, then we construct some vector space. You have some where you can embed either words and/or phrases in some high-dimensional space, and you can use your favorite thing. We've been using pretty vanilla stuff that works reasonably well, but we've also tried using word2vec. This is like the latest thing, right? This is one of these deep network models out of Google where you can now get vectors for a very large vocabulary of words by just downloading it from Google, and we've tried using that. So I don't really care how you build this vector space, how you map words or small phrases into vector space. Just give me your vector space after you've built it, and I'm going to use it together with the logical forms for these sentences to construct a set of soft inference rules that I can use to reason about that text. So that then creates some knowledge base or rule base. And we can also add other stuff to the rule base. We've added stuff from WordNet, from these paraphrase databases. So I guess what CCB, Chris Callison-Birch was just here a few weeks ago, right? He talked about PP, the paraphrase database. We're currently in the process of integrating that in. So we can just throw those rules into the Markov logic as well. And then we give that the logical form, the rule base, and then we ask some inference problems. So the two inference problems that we've looked at, just because they're sort of nice data sets to evaluate on, are textual entailment. I give you two sentences. Does one logically sort of imply or entail the other one? And the other one is this new task maybe a lot of you haven't heard about called Semantic Textual Similarity. We've also done that. And there are data sets then that tell you how do people judge the similarity of sentences. I'll talk a little bit about that later. And then we put that all into the Markov Logic or PSL inference engine, and we get some results saying how likely is it that this sentence entails this sentence, or this text entails this answer, or whatever sort of other inference problem you want to do. OK, so here's my simplest little example. This is data that actually came from, one of the reasons why I'm here at Microsoft is I had a PhD student who like 4 years ago did an internship here with Bill Dolan. And they built this interesting data set where they had people annotate a whole string of YouTube videos with sentences in all sorts of languages describing what was going on, which is particularly more interesting in my work on language and vision, which I talked about at UW several weeks ago. But we actually also use it here because it's been used for RTE problems in STS, because the sentences, two sentences that describe the same video, they're likely to be sort of paraphrases of each other, at least semantically very similar. So this is an actual example from that data set where one person describes a video as a man is cutting a pickle. So Boxer produces this sort of nice, sort of simple logical form for that. There exist three entities, X, Y, and Z, where X is a man, Y is a cutting event, Y is the agent of X, Z is a pickle, and Y is the patient of Z. And then another person describes it as a guy is slicing a cucumber. And we get a similar logical form for that. There are three things: a guy, a slicing event, the guy is an agent of the slicing event, and the cucumber is the patient of the slicing event. And then we just want to know, well, what's the, does one entail the other? Or you could ask how similar these sentences are in semantics according to human judgment. And so we pose this as a logical inference problem where we say, in probabilistic logic, saying what's the probability of that hypothesis given the premise? OK, now if we just did this in first order logic, there's no connection between the words in those two sentences, right? So it doesn't have any way to infer that. And that's where we bring in the distributional rules, of course. So for every pair of words, where A is in sentence 1 and B is in sentence 2, we construct a soft inference rule saying A implies B. But we put a weight on that, which comes from the vector space. So we say that weight is a function, and we've tried various functions here. We use this sort of log odds ratio thing usually, but we're playing around with that. We want to map the cosine similarity of the two vectors for those two words into a weight for Markov logic. And that's one part where I'm not too happy with this formula, and we have some ad hoc ways of doing that. And that constructs all sorts of rules. Some very reasonable ones, like a man implies a guy, and cut implies a super, and slicing, cut implies a slicing event, pickles imply a cucumber event. But we also get man implies cucumber, pickle implies guy, all the other combinations. But of course, hopefully the weight, the vector space, says, well, mans are really not like cucumbers, so that's a very low-weighted rule. So we get a whole bunch of inference rules, and we throw that into the Markov logic. But now we're exploiting all that implicit knowledge in the vector space by doing that mapping. OK, so is that clear? We also do this for phrases. So I really strongly don't believe you can cram the meaning of a whole sentence into a vector. But for short phrases, I think that's not an unreasonable thing to do. So there are various approaches to trying to capture the semantics of at least phrases, some like noun phrases, as vectors. And we also do this. So if we have a phrase like a boy, say, a boy is playing and a little kid is playing. We want to be able to capture the semantic relationship between those. And to do that, we really need a kid, something relating the noun phrase boy to the noun phrase little kid. And so we also build these phrasal rules, like boy implies little kid, with a weight between boy and the phrase little kid. Well, where do we get a vector for the phrase little kid? Well, this is where we bring in all this stuff on compositional distributional semantics, and we use a very simple technique. So a bunch of people have explored what's the right way to compositionally compose vectors to get representations of phrases. We're just using something very simple that a student of Morella Lapata suggested a number of years ago, which is just the dumbest thing you can imagine to compose two vectors, which is just add them up. So we get the vector for little kid by just adding up the vector for little and the vector for kid. And there's a lot of recent work on this using word-to-word vectors. And doing these simple sort of arithmetic operations on these distributional vectors can actually give you some interesting, reasonable results sometimes. And then we just use that as the vector for little kid. So we build for every noun phrase, and we build these vectors for phrases, and we also put in those distributional rules. And like I said, we can also bring in paraphrase rules. So right now we have encoded a set of paraphrase rules that Jonathan Brandt put together, where you get these rules. There are lots of ways of mining paraphrase rules. Again, if you came to CCB's talk a few weeks ago, you learned about his approach using bilingual text, right, to learn paraphrase rules. Where, like I said, we're currently in the process of including PPDB in all of this. But we currently have coded have mapped these Brandt rules where you get something like X solves Y is maps to X finds a solution to Y. And we have various techniques for mapping those to soft logical inference rules. So again, like one of the things I like about these probabilistic logic is you can throw in all these independent, uncertain sources of knowledge, throw them all into the mix in the probabilistic logic, and get coherent probabilistic reasoning out of the whole thing.
So do you parse those phrases with box to get a structure?
Yeah, very good question. And the answer is yes. And we're currently, that's why it's taken us a while because the rules in PBDB are a little bit different than Brandt's, and so we're figuring out how to pipe that through our pro pipeline and get these logical rules out from his paraphrase rules and map their weights appropriately. And so there's a lot of games that come into how you map these resources into probabilistic logic rules. But I think it's always possible, but the details are certainly important and can be complicated at times.
Is there any search involved in these rules? Like, do you dump you presumably don't dump the entire PPDB or parents rules in there?
Yeah, so what we do for those paraphrase rules, we use Lucene to do an IR query on the two sentences to bring up all the paraphrase rules that have, rules words that overlap with those. So we do a standard information retrieval query to find what paraphrase rules are relevant to the cases that the sentences we're reasoning about, and then just bring in the rules for those. So that's a good point, because you can't want to sit there and map all of PPDB. So it's Katrin likes to call this constructing a knowledge base or rules on the fly. So we got a new problem. We use all the resources to sort of put together a knowledge base specifically to reason about that text by, querying, various sources, including distributional knowledge base, a paraphrase knowledge base, and then just pull out the stuff we need, build a set of clauses for that, and then throw it all into the inference engine. Yeah, that's a fair point. So you're only going to get immediate connections then. There's not going to be chaining on that knowledge base. Now again, that's an efficiency issue. If you could do chain if you're just willing to dump everything in, but of course that's not tractable. But that's a fair point. Yeah.
So you get the vector space similarity gives you the probability of similarity or entailment between words or small phrases. To go from that to weights for MLNs or PSL, is there something that?
No, like I said, that's a bit of an ad hoc process at this point. I didn't even put the real formula that we use for MLN. So and that's what we're wrestling with, because these different sources come with different, like PPDB comes with these numbers attached to these rules. How do we map those numbers into coherent, MLN weights? And again, I mean, I think that's a tricky problem, but MLNs are relatively robust as long as the thing is, we've been thinking of doing some training to establish like a linear weighting between these different sources so that they're all mapped to some coherent space, but we haven't done that yet. Okay, so what have we used some of these things for? So I really think I'm much more happy with the framework as a whole than I am with any particular implementation or set of results we have at this point. I very much view this, I should have mentioned this in the beginning, this whole thing is very much work in progress. And so unfortunately, I don't have like state-of-the-art results on a new corpus. So we just competed, I actually didn't include those results in this talk, I should add them. And there was a competition this year at Semival called SIC for Semantic something compositional knowledge. We did okay. We were sort of in the middle of the pack, but we're now doing error analysis on that. So that has both RTE examples. For every pair of sentences, you get both an RTE rating from human judgments and a so-called STS, which I'll talk about, Semantic Textual Similarity rating. And then you can compete with other people on how well you do RTE and STS over this corpus. And our results are sort of middling so far, but we've been doing error analysis, and we really believe that the framework itself is not the problem. It's just we don't have the right knowledge resources and the right mappings of weights and other things to get it all to work properly. So I'm very much sort of disappointed in the current results, because I'd like to have state-of-the-art results. We don't have that, but I still believe in this framework enough that I think eventually we'll get there with some more engineering. And these are some old experiments we ran with standard old RTE data sets, where there's 800 training pairs and 800 testing pairs. One thing we looked at that I think is another nice thing about using probabilistic logic is, so Boxer outputs one logical form, but its underlying is depending on a CCG parse for that sentence to get that logical form. That parse could be wrong. But you can use multiple parsers and get multiple logical forms that are the most probable set. And I can put those into the MLN with different weights. So that's again a thing I like about the probability. You just, you're uncertain about the parse? Okay, we'll just encode that uncertainty into the Markov logic, and it'll be a part of the inference that goes on, and it'll hopefully all be coherent. So we did play a little bit with doing that, and so these are just some initial results. So Johan originally competed in the original RTE using a sort of purely logic sort of approach. This is our MLN approach out of the box, and then we use multiple parsers and encode the uncertainty in the top, I don't know how many parsers, maybe we use the top 5, I think, here. And then we put in these Brandt paraphrase rules. We've now added WordNet. We haven't run that on RTE. But and as we add more knowledge sources and we add more uncertainty in the parsing, we get better results. But again, these are not really state-of-the-art results at this point. One thing that we've wrestled a lot with in Markov logic, as I mentioned before, is the efficiency of inference. So a lot of these problems, once we encode them, it turns out once you get some interesting quantifiers in the language, that really creates a terrible set of MLN inference problems. So my student, Islam, has been working on various techniques for improving the inference. So we had a star AI. So the statistical relationing morning workshop, it sometimes turned into the statistical relational AI workshop, and people call it star AI. And so we had a paper there on the things we've done to make our Markov logic run more efficiently. I'm not going to go into the technical details, except I'll just show you some results. We got some dramatic improvement. So we give each problem a 30-minute timeout. And alchemy out of the box, it doesn't even solve, it only solves 4% of our problems. This is from this SIC evaluation from this past year's Semival competition that I mentioned, in less than 30 minutes. But if we add these optimizations that we've created for alchemy, then we've got that down to it's solving 98% of the problems in less than 30 minutes. And correspondingly, it's doing that in 7 seconds, and we are getting like 72% accuracy on this SIC RTE data set. So we've been working a lot, like a lot of people, on making probabilistic inference in probabilistic logic more efficient, and there's plenty of room for further improvements there, because it does have a tendency to just explode when you just throw arbitrary stuff at it. So, semantic textual similarity, I'll just talk quickly about this. If people haven't heard of this, has been a competition that's going on for a couple of years now. It was a semival track for the first time, I think, two or 3 years ago, where people are given 2 sentences and they're asked to rate the so-called semantic similarity on a scale of 0 to 5, and then the gold standards are averaged over multiple human judgments, and then you get evaluated, and you have to produce semantic similarity scores for these pairs of sentences in the test set, and then you get correlated with what humans said were the semantic similarity of those, and you get a Pearson correlation number, I think, is the number that people finally report. And these are just some examples, because they actually use this paraphrase, Microsoft video paraphrase data set that I mentioned that my former student was involved in the construction. So these are some examples, I think, from that data set and the ratings that humans gave them. We had to do a few things to make this work because we had to sort of soften how we interpret conjunction. So in one case, I have a man is driving and a man is driving a bus. That doesn't, the first one doesn't imply the second because we're missing the information about there being a bus. So what we did was we just broke these into what we called mini clauses, where for every portion of the sentence, like the man is the agent, the driving is the event, the drive is the patient has a patient, and so forth. And we broke those into clauses, and then we combined the evidence using a technique called average combiner in Markov Logic that Natarajan developed. And we also, so this is evaluation in MLN on this. Again, if we use logic only, we don't get that great, but if we add all our lexical rules from distributional semantics, and then we add the phrase rules in, we continue to get a little bit better on this corpus. And this is where we switch to PSL. So I think PSL is a better formalism for doing semantic similarity. MLNs are better at doing textual entailment. So we switched to PSL. We have a paper on this at ACL this past year. But we had to change how we interpret conjunction, because again, so the sort of max interpretation didn't map very well to how people judge similarity of these things. So we mapped this to more of an average rather than max. So we take the interpretation, the truthiness of a conjunction is then an average of the truthiness of each of the individual conjuncts. And ideally, you would want to weight that and learn what weights, because one example I like is a black dog more similar to a black cat or a white dog? It's more similar to a white dog, presumably, because we think of the noun as being more important to similarity than the adjectives, right? So ideally, it would learn to weight different parts of speech to say, well, the noun in a noun phrase is the head. It controls the semantic similarity of the noun phrases. So we have ideas about how to do that, but we haven't done that yet. And the nice thing is, if we do average, it's still a linear function, so it still goes through the linear optimization fine, and it still becomes a linear program to solve the MPE problem. And these are a number of results where we played with different approaches to doing semantic similarity on these different corpora that people have annotated with semantic similarity scores, and showing that the PSL approach, this is without any distributional rules. So DIR means distributional inference rules, I think. So this is without distributional. This is with the distributional inference rules. This is if we actually build an ensemble of a simple distributional technique with our probabilistic logic system. And as we do these things, we get better results. But like I said, I'm still unhappy with it. We're not getting sort of state-of-the-art performance on many of these corpora. But this just shows you that PSL is so much quicker than MLNs. It's nice thing about having that inference that's a linear program is inference is extremely efficient, and we can solve most of these data sets in seconds rather than quite a few minutes that it takes for the MLN. And a lot of the MLNs still time out after 10 minutes. Okay, so I think I want to wrap up now. So again, there's always issues with inference and probabilistic logic. I think there's still plenty of room for improvement there using the latest so-called lifted inference techniques. Improving the parsing into logical form is always a challenge too, and there's active work. Like I said, Johan's even continuing to improve. He just released a new version of Boxer. It didn't actually help us. I think my student ran at least a couple of these tests, and it didn't really help us a lot. Improve the extraction of distributional phrases. Well, this is something that one of the students on the project had a paper with this summer. Is say you have animal and dog. I can build a vector for animal. I can build a vector for dog. the current way we're doing things, it weights the inference rule animal implies dog exactly the same as the inference rule that dog implies animal, right? Does that sound good? No. So what you really want to do is have an asymmetric mapping. So there's now techniques for detecting hypernyms and meronyms from distributional information. So this is a little task that several people have worked on. How can we just know that something is a hypernym of another word or is a meronym of another word by just the distributional context in which those words appear? So there are newer and newer techniques for doing this. And once we do that, we can build asymmetric weights. So now we can have the rule that dog implies animal be much higher than the rule that animal implies dog. That'll have a weight too, but it'll be much less than dog implies animal. So that's a Culling paper, if people are interested. It's a nice piece of work that shows that you can actually learn meronyms and hypernym relations from distributional information. And there's I don't know if people know the work by, I'm losing my mind. He does a lot of work in distributional semantics. He's in Italy. Why am I? Yeah, the Marco Baroni. So they built this data set for detecting hypernyms and meronyms and other things from WordNet in distributional information. And they have this corpus. And now this student that works with Katrin and I, Stephen Roller, has the best results on detecting meronyms and hypernyms using distributional information. We're currently in the process of putting that all into this Markov logic approach to meaning. And of course, adding additional knowledge sources. I mentioned that several times. OK, so just to wrap up. So I'm really a believer that both traditional logical approaches and distributional approaches have advantages, but they also have weaknesses. And I am a big fan of combining these. And like I said, Mike's one of the few other people who have actually looked at this space of combining distributional and logical approaches. And I think that's a very rich area beyond just the stuff that we're trying to do. But what we're focused on is how can we use probabilistic logic to form that, to do that integration. And I think it's a very powerful, very general framework for doing that, because we can produce all sorts of knowledge sources in a uniform, rich knowledge representation that is uncertain, and then perform coherent, global probabilistic inference on that. Again, doing that efficiently is tough, but there's constant progress on making better inference algorithms. And like I said, I think we have promising results, but we still have a lot of engineering to do to turn this into something that really gives us state-of-art performance. But I think the framework is general enough and powerful enough to do that. We just need to invest some more energy in it. OK, thanks.